we know that potential energy of a system is given as U is equal to minus G M m upon R, where the convention is that U is equal to 0 for infinite separation. In our case, that is the Earth satellite system, R is the radius of the satellite's orbit, and let us assume it to be circular for now, which actually is also the case. That is, most satellites have circular orbits. And here capital M is the mass of Earth and small m that of the satellite. So now let us find the kinetic energy of the satellite as it orbits the Earth in a circular orbit. For this, we make use of Newton's second law, F is equal to ma, and put the gravitational force Gmm upon r square for F, because that is the only force acting on the satellite, and for A we substitute v square upon r, that is the centripetal acceleration the satellite experiences. Then if we rearrange this equation a little, what you get is kinetic energy K, that is half mv square, equals Gmm upon 2r. But then since U is equal to minus Gmm upon r, we find that K equals minus U upon 2 for a circular orbit. So if a satellite has potential energy U equal to minus 1000 joules, its kinetic energy K is the negative of it divided by 2, that equals 500 joules. And you see, this equation also gives us the speed of the satellite, that is V is equal to root of Gm upon r. And this relationship tells us something interesting. That is, it is not possible to choose both the radius r of the orbit and the speed v as well independently. That is to say, if you choose radius r, the speed v automatically gets fixed from this formula, and you can have no other speed in that orbit with radius r. Also, an interesting thing to observe is that in this formula, the mass of the satellite does not appear. That is, the velocity of a satellite is not affected by its mass. So if you have a satellite of 100 kilograms placed 200 kilometers above the Earth, it will have the same velocity as, let us say, a 500 kilogram satellite put at the same distance from the Earth. Or putting it a little more dramatically, if a satellite were split into two equal parts without altering the radius r of its orbit, both halves would continue to travel at the same speed as the original satellite. This also explains why astronauts float inside a space shuttle. And the reason is that both are essentially satellites of the Earth, that is, the spaceship as well as the astronaut. And they're moving with the same speed or velocity along the same orbital path. And this shared motion eliminates any contact force between the astronaut and the shuttle walls, resulting in what we call apparent weightlessness. Now, we can also find the time period t of a satellite moving at a velocity v. So, v is equal to 2 pi r upon t, and putting v is equal to root of gm upon r here, we get root of gm upon r is equal to 2 pi r upon t, or t equals 2 pi times square root of r cube upon gm. And you see, this expression is in fact a specific case of Kepler's third law, which states that the square of satellite's orbital period is proportional to the cube of the radius of its orbit. Now, let's calculate the total mechanical energy of the satellite and uncover some fascinating insights about its motion. So, we know that E, or the total mechanical energy of a satellite, is K plus U, that is kinetic energy plus the potential energy. And this equals GMm upon 2R plus minus GMm upon R. Or, if you simplify, E equals minus GMm upon 2R. And we can see here that since K is equal to GMm upon 2R, the total energy E is the negative of the kinetic energy K. So a satellite that has potential energy of minus 1000 joules would have kinetic energy of 500 joules, and the total mechanical energy E would be minus 500 joules. Now, this equation holds very well for an elliptical orbit as well. So, if the semi-major axis of the elliptical orbit is A, we can put A in place of R to get the total mechanical energy as E is equal to minus GMm upon 2A. Another thing to observe is that the total energy of a satellite depends only on the semi-major axis of its orbit and has nothing to do with its eccentricity E. So if you take 3 orbits with the same value of semi-major axis, then a given satellite would have the same total mechanical energy E in each of the 3 orbits. However, if the R value or the A value for a satellite is changed, the change in kinetic energy, potential energy, and the total energy would look like this. And you can see that as R increases, the kinetic energy decreases, and therefore the orbital speed also decreases. Also, you can see here is that for any value of R, U and E are negative, but the value of K is positive. Also, E is equal to minus K. And as R tends to infinity, all 3 curves tend towards 0. So if you take a satellite at low Earth orbit, say R is equal to 7,000 kilometers, it would have much more negative potential energy and higher kinetic energy than one at geosynchronous orbit, which typically is at about 40 to 42,000 kilometers, where everything moves more slowly and has less negative energy values. In essence, the motion of a satellite, its speed, energy, and time period is governed entirely by its distance from the Earth. Once you fix that distance, everything else falls into place, except the satellite, of course, which stays perfectly in orbit.